topic of the talk is global warming and local air pollution have reduced BTs in India. And we'll see why over the course of the talk. So, why is wheat important? With annual production greater than 92 million tons, wheat is India's second largest crop. It accounts for about 50% of the wheat supply. And what did we in the study? We did regression analysis of data from all major wheat districts of India, examining the effect of temperature, solar radiation on rainfall on yields. The study period is 1981 to 2009. So, estimates from models with discrete fixed effects and linear time frames indicate that a 1 degree increase in average daily and maximum and minimum temperature tend to lower yields by 2 to 3% each. And solar radiation has a 1-to-1 positive effect on yields. So, at the outset, I would like to establish the link between solar radiation and aerosol pollution. So, solar radiation is affected by the presence of aerosols in the atmosphere. What are aerosols? Aerosols are a complex mixture of solid and liquid particles suspended in air. Examples include particulate matter, dust, sulfates, nitrates. An important characteristic of aerosols is their ability to influence the amount of solar radiation passing through the atmosphere. This they do it in two ways, by either absorbing or scattering solar radiation. Aerosol optical depth is a quantitative measure of this extinction of solar radiation by aerosols. So, an AOD value of 1 indicates very hazy conditions, and values close to 0.1 indicate a crystal clear sky. So, a recent study by Padma Kumari et al. Using monthly data on surface solar radiation from 12 weather stations estimates that over the period 1981 to 2004, solar radiation reaching the ground decreased by about 0.86 watts per meter square per year. And authors conclude that AODs and cloud contributed to this trend. So, therefore, by decreasing aerosol pollution, we can increase the amount of solar radiation reaching the Earth's surface. And our regression results signal that this pollution reduction may have benefits for wheat productivity because we found a 1-to-1 relationship between solar radiation and wheat yields. But an increase in solar radiation would also lead to an increase in maximum temperature, more solar radiation coming in, higher maximum temperature. And the reduction in aerosol pollution would also lead to more radiation escaping the ground during the night, and this would lower minimum temperature, with consequent indirect effects in the yield via these two variables, right? So this, I will elaborate on this in the coming slides. So what are the, taking all these indirect influences into account, we estimate that a 1 standard deviation decrease in AOD would lead to an increase in yield by 4%. And we find this difference to be statistically significant. So, here's some evidence for reducing air pollution on yields. What are my other findings? The maximum and minimum temperature during the wheat growing season has increased by 0.7 degrees Celsius and 1 degree Celsius. And wheat yields in India would have been higher in 2009 by 4.8%, and if this temperature increase had not occurred. Results of the estimation of the impacts of future climate change predict even higher losses. So, ranging from 12.3% for winter climate change and up to 17.4% by 2070. So, what's the study area? So, the major wheat growing states of India: Punjab, Haryana, UP, Uttarakhand, Bihar, Rajasthan, Madhya Pradesh, Maharashtra, and Gujarat. We merged new districts into their parent districts in order to have a balanced panel so that within district variation is preserved. And variables are area weighted averages of the new districts comprising of parent district. Data are, so district level data on agricultural outcomes was primarily from two sources: the CMI database, Center for Monitoring the Indian Economy, and statistics released by the Ministry of Agriculture. Daily credit data on temperature and rainfall was obtained from IMD. So when I say 1 degree by 1 degree grid, I'm referring to an area approximately 111 kilometers by 111 kilometers. And daily credit resolution data on the AOD, aerosol optical depth, was obtained from the daily level reanalysis data on surface solar radiation was from the MERA database. So, actual data on surface solar radiation, it was only available from 12 weather stations across India, used in the Padma study. But if you want data at a much more spiral level, you don't have any other option but to use this reanalysis data, which is a model output data. So it's not observation. So we constructed the area-weighted average temperature, rainfall, and solar radiation of all the group cells that intersect a 1981 district. So we got the comparative data with the district level data using this. And daily temperature and solar radiation variables were averaged over the growing season in each year. And rainfall was summed over the growing season in each year. And the growing season varies from state to state, beginning a little earlier in northwest India. And data on dates of growing season was obtained from crop calendars published by now. Correlations between the variables. So maximum temperature and log solar radiation were positively correlated. As expected, maximum temperature and minimum temperature were also positively correlated. Maximum temperature and rain were negatively correlated. And maximum temperature and solar radiation, well, there's a correlation, I don't think it's
That's shared.
Yes, the last variable. So this row indicates maximum temperature, and it will not see correlation with any of the variables. This is maximum temperature, maximum temperature. The first set of regression results. So we find that for a 1 degree increase in maximum temperature, PTs decrease by 3%, even for minimum temperature is about 3%. So they both have magnitude similar. How do these columns 1, 2, and 4 differ? In column 1, I have a linear trend. Column 2, the linear trend is replaced by a quadratic trend. In column 3, the linear trend is replaced by a linear trend by state. And in column 4, we have a quadratic trend by state. But all columns control for discrete fixed effects. So we are controlling for any unobservable discrete characteristics.
Can you remind me of the time period?
1981 to 2009. With solar radiations, the results are not so robust as we move from one specification to the other. Similarly for minimum temperature. So the linear trend is replaced by linear trend by state of significance. Here we just see the effect of adding in variables one by one. So in column 1 you have maximum temperature only. You add minimum temperature, the effect stands reduced. But the important point to note is that if you omit solar radiation, then the coefficient of maximum temperature is almost reduced by half. So omitting solar radiation, by omitting solar radiation, you are underestimating the effect of maximum temperature. Why do I want to stress on this? Because a study by Lovell et al. Uses country level data for the period 1980 to 2008 and found that heat in India they have declined by 9% in response to 1 degree increase in maximum temperature. So they have a country level panel. The authors do not control for solar radiation, an important compounder. So they would have even estimated a higher number, given solar radiation's positive correlation with maximum temperature. So a possible reason for this overestimate is because from the country level data, it may not be possible to disaggregate the fact that Indian heat is largely irrigated and is known at relatively high temperatures. Now coming to the effect of reducing pollution on yields. So that's the total impact, and it works through 3 channels. One is solar radiation, one is maximum temperature, and one is minimum temperature. So to get the effect of, to get this partial derivative, we can get it directly from this regression, and we're using the coefficients in column 1. So we have a linear trend and discrete fixed effects. So all these coefficients are estimated from the yield regressions. Whereas to get the effect of log solar radiation on AOD, maximum temperature on AOD, and minimum temperature on AOD, EOD. They are obtained from regressions of log solar radiation, maximum temperature, minimum temperature, or aerosol optimum. So, data on daily gridded EOD is available from the year 2000 onwards only. So, therefore, the period for this analysis is 2000 to 2013. We regressed max D and min T with grid fixed effects and a quadratic day of the season trend. The estimates these are the estimates we got. So we got AMD and log solar radiation to be negative peak. As AMD increases, solar radiation decreases, which is likely because AMD blocks incoming solar radiation. And similarly for AMD and maximum temperature, AMD and minimum temperature become positive. This effect being large for long time. This effect of minimum temperature outcomes the effect of maximum temperature. So substituting all these results into this expression, we find that the direct impact on the yield, we find that the total impact on the yield, taking all these direct and indirect impacts into account, to be minus 0.19 with a 95% confidence interval of minus 0.29 to minus 0.06. So given the standard deviation of AMD 0.24, this translates into an increase in yields of 4% for one standard deviation change. So if you change AOD by 0.24, you're going to get an increase in yields of 4%. Any questions so far?
The effect of rainfall was its
No. Incident. Yes. Yes. I just asked.
because of the
Yes. So for instance, if you see this column, right? So if you compare column 4 with 5, column 5 doesn't have share indicated as a control, right? Column 4 and 5, 4 doesn't have share indicated as a control, whereas 5 does. But if you see these impacts don't change that much.
Do you want to take technical questions now or at the end? How have you measured the outcome variable yields measured?
It's in tons per hectare.
But I mean across what types of crops or
It's just wheat.
Was there any need to track the yield data series? Because they might have been increase in technology better.
So that's why we have a linear trend. We're controlling for a linear time trend, that kind of difference. So far, we've allowed for a linear relationship. So to allow for a non-linear relationship, we experimented with a quadratic specification, but the fit was almost linear. We also modeled the mean temperature using restricted cubic splines, and this is the fit. This is the resulting fit. So as you can see, it's not dramatically non-linear, it's less linear, but there's a difference in slopes at the lower end and the upper end. So there's some evidence that the impact of temperatures on yield is, that high temperatures are more harmful to yield productivity than maximum temperatures. And the difference in these slopes was statistically significant at the 5% level. This is consistent with experimental studies that find that temperature increases are more harmful for wheat productivity at high temperatures. And to test whether there's a threshold temperature above which the response of yields to further increases in temperature is more pronounced, we model the log of yield as a piecewise linear function of growing degree day and heating degree day. So what's a degree day? Well, in the literature, growing degree day is a measure of accumulated exposure to a given range of temperatures throughout the growing season. So suppose on a given day temperature was say 27 degrees Celsius, so that day contributes 22 growing degree days. So for each day you calculate the growing degree days for that day using this, and then you just add up all those growing degree days over the growing season. Of course, a question is that temperature doesn't stay constant at say 27 degrees or any 22 degrees at any given day, right? It changes throughout the day. So this then you just fit a sign curve. So there's a complicated measure method to determine the growing degree days for each given day, but this is the essential idea. And for each day you find out the growing degree days and you add them up throughout the day. Similarly, heating degree days are defined as this, so in temperature. This is basically the baseline threshold here is 27 and there is 5. So you assume that below 5 degrees Celsius, heat doesn't grow. So temperature is below 5 degrees Celsius on any day, the plant won't grow. So that day contributes 0 degrees. But any addition over 5, any temperature over 5 degrees Celsius will contribute to growing degree day in this manner. Similarly, here the threshold is 27. How did we figure out these thresholds? This was just determined by talking to agricultural scientists and reading agricultural literature. And 27 was determined by looking over several thresholds and choosing the one with the best odds.
What does it mean it doesn't grow? I mean, if we don't grow it, the crop doesn't.
The crop will not, people will grow. So if you plant wheat at a temperature below 4 degrees Celsius, the plant will not germinate.
We should affect it.
Yes. So here are the results of growing degree days. As you can see, heating degree days do have are more detrimental than growing degree days, but we don't find the effect statistics. Right? And even to test whether these coefficients are equal, we cannot reject. So these coefficients are equal, so we reject them out. So we essentially find that heating degree days matter, but that may be because we don't observe many hot days in the data. So actually, the highest threshold and the highest threshold for average maximum temperature is 33 degrees Celsius. So because we don't observe many hot days within our data, we're not able to reliably estimate the impact of those hot days on
So the higher the temperature relative to 27, let's say, the worse it is for the week.
yes.
So
You expect that, yeah.
that seems to be like monotonic in this difference, how much higher, right? But then I would assume that if you actually have 5 degrees, which you just pointed out, that's actually the worst case. So then the thing will not grow at all.
That's the bench, that's the baseline threshold, right? So that way you're really doing it, but it's not really harming the crop because the crop isn't there. But suppose the crop is out there, right? So it's a piecewise
When
linear
you say it doesn't harm, so if it does not germinate, isn't that a part of the heat? That the plant doesn't yield a certain thing at the end of the season.
Yes, but we expect temperatures to go up, right? And the temperatures in any place will not stay at 4, right? You're just monitoring. Basically, why was the concept of growing degree days developed? To see that at what stage a plant will grow, at how many degree days a plant will grow, right? So,
So I mean, delay in the beginning has an impact.
yes,
I mean, in which case it seems the lower the value, it seems that at 0 it's really bad in terms of growing.
yes.
And then above
But
27 is
yes,
really bad.
yes, if it stays at 0 throughout, yes, it's very bad. But you would expect that at any place temperatures would grow over time.
Just how it's measured.
So, I mean, the reason I have them separately in here is because you expect the effect of GDP to be different from that of each degree. So, above 27, you expect the threshold to change, you expect a gain. So, yeah, so far I had a linear time trend but not year fixed effects. If I substitute the linear time trend by year fixed effects, then minimum temperature and loss solar radiation are no longer significant. But yes, the coefficient of maximum temperature goes up. So you see that maximum 1 degree increase in maximum temperature decreases yields by about 5%. So the results are not as robust for minimum temperature and loss solar radiation as they are for maximum temperature. Now, in fact, impact of past climate change on current yields. So, temperature has trended over the period 1981 to 2009, and the question of interest is how these growth would have evolved without this trend. So, we trended minimum and maximum temperature as follows for every district at IT. For every district in the panel, I ran a regression of that district's maximum temperature on a linear time trend, got the predicted values, which is T star 90, and then from the current observation of the district for that year, subtracted the predicted value and added the predicted value for 98. So to get T trending temperature, both for maximum and minimum temperature.
Is the sheer variation exogenous? I mean, is it that the past temperature flows actually make people, maybe because of gravitation or whatever, make people invest in irrigation in certain ways? Or is that a completely separate public policy?
Actually, it's really fixed events.
Or it's lag dependent, it's a lag effect. So, the fixed effect is only in some sense taking care of.
Just the district level.
Yeah,
I would say
just what.
I mean, I would say it's a public policy issue. I don't think people are, because people are using, because they expect in any case that in a given year wheat is largely an irrigated crop, right? It's not like rice, which is a main fed crop. So I think they're used to the same cycles and then whichever their range is. It's not so dependent on rainfall. In that channel.
But you have a variable which is shared.
Yes, they're controlling. And also, as you saw, the results didn't change much in this period. So, by the end of the period, the production weighted maximum and minimum temperature in the wheat season increased by 0.7 and 1 degree Celsius. And we compute the difference between predicted yields with observed weather and predicted yields with trended weather. And predicted yields were calculated using the parameters from the linear model for the district fixed effects and linear time trend in column 1. And to arrive at the national effect, the production weighted average of these differences was taken. And the result was that the yields in 2009 were lower by about 4.8% when the trend in maximum temperature. 95% so already we have seen the impact of climate change based on this forecast. The impact of predicted climate change on future yields. So climate change predictions are made from the Regression 2.3 model. This is a regional climate model, and therefore it provides climate simulations over a final spatial resolution, 1 degree by 1 degree, and we obtain monthly model output on both maximum temperature and minimum temperature. We are not seeing the effect for solar radiation because the model output estimates are unreliable, because aerosols are not modeled very well. So those predictions are not reliable. And we consider the R58.5, which is a high emission scenario for climate change. Regional climate. Okay, so climate change impacts are computed for 3 time periods: near future, which is 2040, mid future 2070, and distant future. And so relative to 1981 to 2009, temperatures in 2040 are going to be higher by 1.25 degrees Celsius average. Similarly for 2070, 1.30. And minimum temperature is 3.04. So increases in minimum temperature will outweigh increases in maximum temperature in the coming decades, and this is consistent with the literature on climate change. It predicts that minimum temperatures are going to increase by much more than maximum temperatures. So we calculated the production weighted predicted yield per hectare for each district year observation after climate change and after current observed weather. These yield outcomes were found across all districts in the sample for each year, and then we computed the percent change in average yield per hectare after climate change and after climate higher effect from the temperature because the absolute increase in temperature has to be so in all cases we were in 2045 by 1.7%, but in 1981 for the mitigation.
You said that the yield was comes per hectare.
Yes.
How is that measured?
It's just data from like for example databases, right? So MOA releases district level data, but you need to ask for 2040, 2000
No. I meant even for your 1981 to 2009.
Yes, it's just district level data which is reported by
And
statistics.
how's that measured?
Okay, you need to say how's that measured at the district level?
Yeah.
So they have these crop cutting surveys. So within a district, they choose some locations where they just measure the yield. So they measure how much is they actually measure yield and then multiply it by area and then they get production. So they just go to a plot, they survey they see plant and they see on the plot and they see how much percentage of the land. So they know the size of the plot.
So you're not including anything in this. What I'm wondering is whether this is picking up, say, this adoption of wheat by wheat words, by wheat. Depending on how wheat yields are measured, if they just take total production divided by the total amount of land that is, well known to have been reported as land growing wheat,
So
then
they don't do that.
okay, so it looks at sample plots, agricultural plots,
Yes.
and goes and looks at each one of these plants.
Not each one, but counts. So the sample selected plots, right? And then so the way these crop cutting surveys, I think these are called crop cutting surveys. So the way it works is that they sample within a plot they see how much wheat was produced, right? And then they have an estimate of the area sold to wheat within that district.
And that estimate of area is from satellite or
No, they just have it in their records.
It's reported up through the chain.
Areas are supposed to be mentioned.
Yeah.
The area is a census, thank you. It's a
Yeah,
Yeah,
census.
it's supposed to be recorded up from each village by the revenue officer in each village and then after the revenue administration.
and that's done every year, every 2 years.
Every season.
Every season. So you're not picking up then any possible effect on adoption or disadoption of wheat as a crop. You're not doing it.
So, what are the caveats of this analysis? States with maximum temperature exceeding 33 degrees Celsius are not present in the data. So, if days with temperatures exceeding this bound to occur, then we are not able to apply our estimates for the effect of such hot days because we don't see such things in the data. My conclusions. So, global warming over the period 1981 to 2009 has reduced wheat yields. Reductions in aerosol pollution that increase solar wind raise yields, but this finding about the potential gains from local air pollution has to be qualified by somewhat smaller and noisier estimates that result when the linear trend is replaced by the quadratic trend. And our preferred specification is the linear model because it preserves the most variation in the data and results indicate that models with quadratic trend are probably not required by integration. And results of the estimation of the impact of future climate change, which losses ranging from 12.2% for predicted climate change and up to 17.4% by 2070. But the above findings seem more optimal adaptation. And if farmers are able to switch to heat-resistant varieties, then damages will be less. So yield losses may be high due to increased occurrence of extreme temperature events expected to occur with climate change.